Gravity. It's one of those things we live with constantly but rarely stop to think about. It's the reason you're not floating right now. The reason the moon orbits Earth. The reason Earth orbits the sun. The reason you can drop a pen and it will fall instead of rise. But what is it really? Let's take a moment to slow down and let this question sink in. Gravity is not just some background force we've learned to accept. It's one of the four fundamental forces in nature. The others are electromagnetism, the strong nuclear force, and the weak nuclear force. Yet gravity is different. It's the weakest of the four forces, by far. And yet it's the most dominant across the vast scales of space. That's part of the mystery. Why does gravity, so incredibly weak on a small scale, end up shaping the entire universe? Let's think about it. The electromagnetic force is much stronger, but it can cancel out. A positive charge and a negative charge? They attract, then neutralize. But gravity? There's no negative gravity. Mass only adds up. It only attracts. It never cancels. That means everything with mass, no matter how small, contributes to the gravitational web of the cosmos. You, me, the moon, black holes, clouds of gas drifting in space, all of it adds a thread to that invisible network. And the more mass something has, the more it pulls on everything else. But the strange part is that we feel gravity all the time, and yet, we don't actually know why it works the way it does. We can describe its effects. We can predict its outcomes. But as we'll see in later sections, its deep nature is still an open question. Now, historically, gravity was one of the first great mysteries that pushed humans to seek universal laws. And it starts in a familiar place. Not in a lab, not on a spaceship, but under a tree, with a falling apple. This is where we'll go next. Let's travel back to the late 1600s, to the English countryside. A young man named Isaac Newton, having left Cambridge due to a plague outbreak, finds himself at home in the village of Woolsthorpe. One day, while walking through an orchard, he sees an apple fall. Now, this is the part of the story that everyone knows. But what makes Newton's story remarkable isn't that he saw an apple fall, it's what he wondered afterward. Why did it fall straight down? Why not sideways or upward? And more than that, if gravity pulled the apple, could it also be the same force pulling the moon in its orbit around Earth? This was a profound leap of insight. Most people at the time assumed earthly physics and heavenly physics were separate. Things on Earth fell. Things in space orbited. But Newton had the radical idea that maybe they're all connected. Maybe a single law governs motion everywhere. So he developed what became known as the law of universal gravitation. Here's the idea in simple terms. Every object in the universe attracts every other object. Everything pulls on everything else. Not just planets and stars, but you and me, your phone, the pen in your hand, every atom. Now, of course, the force depends on two things. Mass. The more massive two objects are, the more they pull on each other. Distance, the farther apart they are, the weaker the pull becomes. He even wrote the formula for it. F equals G times the product of m1 and m2, all divided by r squared. Where F is the gravitational force between two objects, m1 and m2 are the masses, r is the distance between their centers, and G is a constant, the gravitational constant. This formula lets scientists calculate the gravity between any two objects, from falling apples, to the moon's orbit, to the path of comets arcing through the solar system. It was the first mathematical framework to describe gravity everywhere in the universe, and it worked beautifully. Thanks to Newton, we could finally understand how planets move in elliptical orbits, how tides rise and fall due to the moon's gravity, even how to aim spacecraft in the modern era. For over 200 years, Newton's theory of gravity was seen as complete. It made sense, it gave answers, it was predictive, it worked. But it had its limits. There were small inconsistencies it couldn't explain, like why the planet Mercury's orbit slowly drifts over time, a phenomenon called perihelion precession. And more than that, Newton couldn't say what gravity actually is. He described how it behaves, but not why it works at all. He himself admitted that he could frame no hypothesis as to what causes gravity. He left the mechanism unanswered. There was still a mystery in the middle of the theory. But it would take another 250 years before someone would take Newton's brilliant framework and turn it completely inside out. His name was Albert Einstein, and he didn't think of gravity as a pull at all. He saw it as something else entirely. For over 2 centuries, Newton's theory of gravity reigned supreme. It explained falling apples, orbiting moons, and planetary motion with stunning accuracy. It shaped everything from physics to engineering. But deep down, something didn't sit quite right. It didn't explain why gravity worked. It treated it like a force that just reached out instantly across space. And it couldn't fully explain strange little details, like the wobble in Mercury's orbit. Enter Albert Einstein. In 1915, Einstein published his general theory of relativity, and with it, he forever changed the way we understand gravity. He proposed something radical. Gravity isn't a force at all. Let that settle for a moment. Gravity, according to Einstein, is not some invisible tether pulling on objects. It's not an action at a distance. Instead, it's a curvature of space and time itself. To understand this, we need to shift how we think about the universe. What is spacetime? Before Einstein, space and time were thought of as 2 separate things. Space is where things are. Time is when things happen. But Einstein realized they are actually interwoven into a single fabric called spacetime. You can think of spacetime as a giant, flexible sheet. It stretches in all directions, and everything that has mass, planets, stars, galaxies, sits on this sheet. Now imagine placing a heavy bowling ball onto this sheet. What happens? The surface dips. Now roll a smaller ball nearby. It curves toward the dip, not because the larger ball is pulling it, but because the surface is bent. That's gravity in Einstein's world. Mass bends spacetime, and objects move along those curves, and it's not a force pulling things together. It's the shape of space telling objects how to move. This is called the geometric view of gravity. It's elegant, it's powerful, and, best of all, it works. How it changed. Our understanding Einstein's equations could explain things Newton's couldn't. Take Mercury. For years, astronomers noticed that Mercury's orbit wobbled slightly. Newton's math almost predicted it, but there was always a small mismatch. Einstein's theory matched perfectly. It also made new predictions. One of the most famous, that light itself would bend as it passed near a massive object like the sun. This was tested in 1919 during a solar eclipse. Astronomers observed starlight bending as it traveled past the sun, exactly as Einstein had predicted. It was the first direct confirmation of general relativity, and it made Einstein a global icon. But there's more. Einstein's theory didn't just redefine gravity, it introduced entirely new cosmic possibilities. Predictions of the unseen. From his equations emerged something wild. Black holes. Regions of space where mass becomes so concentrated that the curvature of spacetime becomes infinitely deep. At a certain point, not even light can escape. Einstein himself didn't believe they could actually exist. But the math said otherwise. His theory also predicted that time itself slows down near massive objects. The stronger the gravity, the slower time flows. This isn't just theoretical, it's been measured. Clocks on airplanes tick slightly faster than those on the ground. GPS satellites need to adjust their timing because of it. It's real. And it comes directly from the idea that gravity affects the fabric of reality. Not just space, but time too. A new way to see the universe. Einstein's view of gravity is a turning point in human thought. He showed us that mass tells space how to bend, and bent space tells matter how to move. It's a universe made not of forces and pulls, but of curves, dips, and geometry. A cosmic dance between space, time, and mass. And it opened the door to a deeper understanding of the universe. From this point forward, we no longer saw the cosmos as a collection of isolated objects. We saw it as a connected structure, where motion, time, and energy are all woven together by the shape of spacetime. In the next section, we'll zoom out and see how this invisible web, this gentle bending of space, governs everything from stars to entire galaxies. Because gravity doesn't just keep us on the ground, it shapes the entire cosmos. Now that we understand gravity as a warping of space and time, let's step back, way back. Let's leave Earth, past the Moon, glide past Mars, Jupiter, Saturn, until the planets are just distant marbles, and the Sun is a glowing dot behind us. Now we start to see the universe on a different scale, and gravity? It's still there, everywhere, quietly sculpting everything. Let's begin with the stars, how gravity builds a star. Stars are born inside nebulae, massive clouds of gas and dust drifting through space. At first glance, these clouds seem still and silent, but inside them, gravity is always working. Slight differences in density cause tiny regions to collapse. As gravity pulls more material inward, the pressure builds. The temperature rises. Eventually, the core gets hot and dense enough for nuclear fusion to begin. Hydrogen atoms fusing into helium, releasing light and energy. A star is born, and it only shines because gravity squeezes it tightly enough to ignite. There's a balance. Fusion pushes outward. Gravity pulls inward. This balance is called hydrostatic equilibrium, and it keeps the star stable for millions or even billions of years. But what happens when the fuel runs out? The death of stars. Gravity takes over. When fusion slows, gravity begins to win. Small stars quietly fade into white dwarfs. Larger stars collapse into neutron stars. The most massive ones die in brilliant explosions called supernovae, leaving behind black holes. In each case, gravity is the final sculptor. It's not just responsible for a star's birth. It decides how the star will die. But stars don't live in isolation. They group together into galaxies. Galaxies, cities of stars built by gravity. A galaxy is a collection of hundreds of billions of stars, sometimes more, bound together by gravity. Our own galaxy, the Milky Way, is about 100,000 light-years across. It's home to at least 200 billion stars, along with planets, dust, dark matter, and gas. And what keeps all of it from flying apart? Gravity. Every star orbits the galactic center. The stars closer in move faster, just like planets around the sun. And deep in the middle of our galaxy, astronomers believe there's a supermassive black hole, over 4 million times the mass of the Sun. This central black hole isn't sucking everything in. It's just so massive that it shapes the orbits of everything around it. Now, zoom out even more. Galaxies are not alone. Clusters and the cosmic web galaxies gather into groups and clusters bound by, once again, gravity. Some clusters contain thousands of galaxies, and between them there's more. Dark matter, invisible scaffolding, that gravity reveals only through its pull. On the largest scale, we see something remarkable. The universe forms a structure, a kind of cosmic web. Galaxies and clusters are strung along massive filaments of dark matter with huge voids in between. Imagine a sponge or the veins in a leaf stretching across the cosmos. This is not random. Gravity is the architect. From tiny fluctuations in the early universe, minute differences in density, gravity built everything we see. It turned a nearly uniform universe into one filled with stars, galaxies, clusters, and cosmic symmetry. A force that connects all things. So whether it's a cloud of gas becoming a star, a supernova scattering heavy elements, a spiral galaxy twirling in the dark, or a vast web stretching between clusters of galaxies, gravity is there. Subtle, quiet, constant. It is the binding force of the universe. It's not loud, it doesn't glow, it doesn't emit radiation, but its influence is everywhere, always pulling, always shaping. Even now, as you sit here listening, gravity is pulling you toward the center of Earth, while the Earth orbits the Sun, while the Sun moves through the galaxy, while the galaxy drifts through the web of the universe. All of it, woven together by gravity. In the next section, we'll shift from the grand scale to the strange. Because as we've said before, gravity doesn't just bend space, it bends time. And the deeper we look, the stranger things get. So far, we've seen how gravity forms stars, shapes galaxies, and binds the universe together. But gravity has another, even stranger trick. It doesn't just shape space, it shapes time. This idea feels almost unreal at first. After all, we think of time as something steady, like a river flowing evenly for everyone. But according to Einstein, that's not how the universe works. Time isn't separate from space. It's part of the same fabric, spacetime. And when gravity bends that fabric, it bends time too. Gravitational time. Dilation. Let's imagine something simple. You're standing on a tall mountain. I'm standing in a deep valley. We both have identical clocks. They're perfectly synchronized. But over time, if we check them again, we'll find they're no longer ticking at the same rate. Your clock, up on the mountain, runs ever so slightly faster than mine in the valley. Why? Because gravity is weaker where you are. The deeper you are in a gravitational well, the closer you are to a massive object, the more slowly time passes for you. This effect is called gravitational time dilation. It's not science fiction, it's been measured, it's real. Time corrections in everyday life. Think of the satellites above us, circling Earth as part of the GPS system. These satellites experience time differently than we do. Because they're farther from Earth's surface, they experience weaker gravity. That means their internal clocks tick faster than clocks on the ground. It's only a difference of microseconds, but over time that adds up. If engineers didn't account for this tiny time dilation, GPS would give incorrect positions, off by kilometers every day. In other words, the GPS on your phone works because Einstein was right. Time isn't absolute. It changes depending on gravity. What happens near a black hole? Now let's take things to the extreme. Imagine you're near a black hole. Its gravity is so strong, its curvature of spacetime so deep, that time slows down dramatically. If you could hover just outside its event horizon, the point of no return, your clock would slow almost to a stop compared to someone far away. This isn't just theory. In the movie Interstellar, there's a planet orbiting near a black hole where 1 hour equals 7 years in the outside universe. It sounds like Hollywood exaggeration, but it's actually based on real physics. A few hours near the edge of a black hole could mean decades have passed outside. This leads to a strange possibility. Gravity might let us travel into the future, just by being near enough to slow down time. It's not time travel in the science fiction sense, but it's a glimpse into how flexible and strange time can be. Gravity bends light, too. But time isn't the only thing gravity affects. It also bends light. We call this effect gravitational lensing. Here's how it works. Imagine a distant galaxy, billions of light years away. Now imagine a massive galaxy cluster between it and us. As the light from the distant galaxy travels toward us, it passes near the cluster. The mass of the cluster bends space-time so much that the path of the light curves. From our perspective, it looks like the galaxy behind it has been stretched or duplicated into arcs and rings of light. These are called Einstein rings, and we've seen them with our telescopes. Gravitational lensing allows us to see galaxies we couldn't otherwise detect, too faint or too distant to be visible without nature's magnifying glass. It also helps us detect dark matter, which doesn't emit light but has gravity we can measure. Gravitational waves, ripples in space-time. And there's one more strange consequence of gravity we've only just begun to hear. Gravitational waves. When two massive objects like black holes or neutron stars collide, they create ripples in space-time itself. These waves travel across the universe. And when they pass through Earth, they stretch and squeeze space ever so slightly. In 2015, we detected gravitational waves for the first time, using incredibly precise instruments called interferometers. It was a milestone moment. For the first time in human history, we didn't just see the universe, we heard it. We listened to two black holes merging over 1 billion light years away. And we heard it in the form of tiny tremors in the fabric of space and time. Time and gravity, intertwined. So let's pause for a moment and reflect. We began by thinking of gravity as a force that pulls things down. But now we've seen it for what it truly is. A bending of space, a slowing of time, a warper of light, a creator of ripples through the very fabric of reality. Gravity doesn't just tell things where to fall, it tells the entire universe how to move and how to change over time. And even though we've discovered so much, the truth is, we've only just begun to understand it. In our final section, we'll talk about the limits of what we know, why gravity still holds deep mysteries, and how solving them might be the key to understanding the future of physics and the fate of the universe itself. We've come a long way in our understanding of gravity, from falling apples and orbiting moons, to warped space-time and galaxies connected by invisible threads, to time bending, light curving, and ripples echoing across the cosmos. And yet, despite all we've discovered, gravity remains a mystery at its core. Because here's the truth. As successful and elegant as our current understanding is, it's not the full story. Let's talk about why. Gravity doesn't fit with quantum physics. Right now, we have two brilliant working theories that describe the universe. General relativity, which describes the large, stars, galaxies, gravity, and the shape of space-time. Quantum mechanics, which describes the small, atoms, particles, fields, and probabilities. Both are incredibly successful in their own realms. Both have been tested to astonishing precision. But here's the catch. They don't agree with each other. The math of quantum theory breaks down when applied to strong gravitational fields. And general relativity doesn't explain the behavior of particles at the smallest scales. Nowhere is this conflict more obvious than in one particular place. The center of a black hole. Black holes break the rules. Inside a black hole, all the mass is crushed into an unimaginably tiny point, a singularity. At this point, our equations stop working. Relativity says gravity becomes infinite. Quantum physics says that can't be. Information should be conserved, but in a black hole, it seems like information is lost forever. This conflict creates the famous information paradox, and physicists around the world are still trying to resolve it. Some believe gravity might be emergent, a side effect of deeper quantum principles we don't yet fully understand. Others are working on ambitious frameworks like string theory, which imagines particles as tiny vibrating strings existing in higher dimensions. Loop quantum gravity, which tries to quantize space and time itself. Or the holographic principle, which suggests the universe might be a kind of projection from a lower dimensional boundary. These are more than science fiction ideas. They are real areas of research, fueled by the mystery of gravity. And the pursuit of unification, the so-called theory of everything, may hinge on understanding it. Dark matter and dark energy. And then, there's the invisible stuff. Roughly 95% of the universe is made up of things we can't see directly. About 27% is something called dark matter, an unknown form of mass that doesn't emit or absorb light but still has gravity. We can't detect it with telescopes, but we know it's there. Because we see its gravitational effects. It holds galaxies together. It shapes cosmic structure. Without it, our models of the universe simply don't work. And then, even more mysterious, is dark energy. Making up nearly 68% of the universe, dark energy is a force that seems to be pushing the universe apart, causing its expansion to speed up. Yes, that's right. Not only is the universe expanding, but it's doing so faster and faster over time. This discovery shocked scientists in the 1990s, and it's still unexplained. Is dark energy a property of space itself? Is it related to gravity on the largest scales? Or is it something entirely new? We don't know. But whatever it is, gravity is once again at the center of the puzzle. The future of understanding. So where do we go from here? We keep asking questions. Can we unify gravity with the quantum world? Can we find the particles or waves that transmit gravity? Can we understand dark matter, dark energy, and the true shape of the cosmos? New telescopes, gravitational wave detectors, and deep space observatories are being built as we speak. And every new piece of data brings us a little closer. Gravity may be silent, but it speaks through motion, through curves, through time itself. And we are just beginning to listen. Final reflection. Gravity and us. Let's bring this home. Gravity isn't just an abstract concept. It's the force that holds your feet to the earth, that makes your cup fall, that carves canyons, raises tides, and pulls the stars together in the night sky. It's what allows stars to shine, planets to orbit, and galaxies to dance. And even though it's invisible, it is everywhere, connecting everything. You, the earth, the moon, the sun, the stars that burned out billions of years ago. We are all moving in the web that gravity weaves. And perhaps most beautiful of all, we, small as we are, have begun to understand it. We've given a name to the force that binds us. We've written its equations. We've followed its curves into black holes and across the vastness of the cosmos. And in doing so, we've realized something profound. We are not separate from the universe. We are part of it, shaped by it, connected through gravity across time and space. Thank you for being here, for listening, and for wondering. Stay curious, stay grounded, and always stay cosmic.